So, ladies and gentlemen, today we are going to talk about something very fundamental, and that's degrees of freedom analysis. Uh, in my personal opinion, it all begins and ends with degrees of freedom. Degrees of freedom. He or she who understands degrees of freedom properly can do process control, process design, process operations, optimal operation, everything very easily. And he or she who does not understand this properly can't do anything. Okay, so this is actually a very important topic, so I'd like to devote maybe a couple of lectures to degrees of freedom analysis. So let's see. Degree of freedom as commonly understood is what am I free to change? How many things can I change independently? So number of variables that can be adjusted independently, that are not fixed, that can be varied. I'm free to move the number of variables that I'm free to move. And traditional degree of freedom analysis is typically done in this way. You count the number of independent variables, and then you subtract out the number of independent material energy balances, number of equilibrium constraints, and equilibrium could be mechanical, thermal, or phase, or even reaction. And then you also take out the number of specifications that are given, and that gives you the degree of freedom of the process under consideration. However, as you can see, this counting business can get very tricky. You may count something twice. Common example, summation xi must be equal to 1. Should it be counted? Should it not be counted? You may count something twice. You may forget to count something. And in the very rare case that all of these entities are properly counted, would you get the correct degree of freedom? And so this method, the academic method, is actually guaranteed to fail. You'll mess up one of the entities, one or more of the entities, and the degrees of freedom that you get would then not make sense, would be unrealistic. And so what we need is a simple and intuitive methodology for degrees of freedom analysis to get the degrees of freedom of a process by inspection of the process. That's the main idea behind this lecture. So let's get going. Let's take the simplest possible process, flow through a pipe, liquid flow through a pipe. So you've got a pump pumping liquid, and at the exit of the pump there's a control valve, and you can adjust the valve position, and as you adjust the valve position, the flow through the pipe will change. So there's a flow controller, and there's a set point for that flow controller. So in this case it's pretty clear. The control degree of, there's one adjustable flow, and therefore the degree of freedom is 1, and that degree of freedom is the liquid flow rate as drawn in the picture. Let's look at a liquid flow network. So there's a splitter that splits an incoming stream into 3 output streams. So first question is, how many control valves will we have? Obviously these 3 control valves. And somebody puts a valve here, there's a problem because you cannot independently set 4 valves because of incompressible flow. You'll require that flow out, total flow out F1 plus F2 plus F3 must be equal to Fin, and therefore you're not free to adjust the inflow, and therefore this valve should not be there. And on each of the other 3 independent valves you can have a flow controller, and each of those flow controllers has its own set point F1, F2 and F3, and therefore the degree of freedom for this process is 3. And as shown in the control system, these the specification variables corresponding to these 3 degrees of freedom are flow 1, flow 2 and flow 3, those 3 set points. So now here you've got a splitter and then a T and a mixer, 2 mixers. So you get these valves. Obviously this is not possible because again because of the incompressible flow constraint, which requires that inflow must be equal to outflow. So this flow over here Uh-oh. Well, so what color shall we use? Blue is good. So, what the hell happened here? Okay, so let's be this. Let's look at this guy. So this flow over here, sorry, yeah, this flow over here, this is over-specified because this flow must be I don't know what's going on. This flow over here must be flow in minus, let's call this F1, and so this is not independent, that is why it has been crossed out. And now let's get back to okay. So here the degrees of freedom, and each of those other independent valves will have its own flow controller, and those flow controllers will have their own set points. So in this case, degrees of freedom is 4, and the way the control system is shown, the 4 specifications corresponding to these 4 degrees of freedom are the 4 flow rate set points. Okay, now let's get to something more interesting. It's, well, not very interesting, but it's actually of fundamental importance in terms of looking at overall plant material balances. So here's a liquid tank, flow in, flow out. You've got inflow and outflow flow controllers corresponding to those valves and their set points. And one may be tempted to think that, oh, the degrees of freedom is 2. Yes, the degrees of freedom is 2. The control degrees of freedom is 2 in the sense that you can set 2 flow set points. But unless flow in is equal to flow out, the process will not be at steady state, and therefore the liquid level will either be increasing or decreasing depending on whether the flow in is more or the flow out is more. And therefore, to achieve steady state, you cannot have both the flows set independently. One of the flows will have to be set by the level in the tank, to stabilize the level in the tank. And I'm showing one possible configuration where flow in is independent and the level controller is setting flow out set point. So in this case, there are 2 adjustable flows, so the control degrees of freedom is 2. There's one level controller, and I wanted you to understand one thing, which is that, see, let us consider a change in flow set point and a change in the level set point. These 2 degrees of freedom as shown in this control system are flow in and tank level. So if flow in is if flow in is changed, what will happen to the level? The level will start to rise, and if the level controller does its job properly, flow out will also become equal to flow in, and the level will, okay. So if the flow in set point is changed, the flow through the entire process changes. That means changing flow set point, flow in set point, causes a change in both the steady state flow, and it also has a transient effect. Now let us consider a change in the level controller set point. So let's say my level controller set point goes from where it is, maybe increase of 10%, so 50% level, maybe the set point goes to 60% level, and let's assume that it's a PI controller. So what will happen is, because flow out has, level set point has increased, in order to cause the level to increase, the flow out, let's say flow out will decrease, and then it will increase back up and get back to the same value, because at the final steady state, because the inflow has not changed, the outflow will remain the same as inflow, so it will come back to 0. So you see, when you change the level set point, the steady flow through the system doesn't change. It has a transient effect, but it has no steady state effect. So this particular degree of freedom has a dynamic effect, a transient effect. It has no steady state effect. On the other hand, this degree of freedom has both a steady state effect and a dynamic effect. Okay, so now that we are looking at degrees of freedom, it's time to distinguish between so there's two adjustable flows. One level controller is required for material balance. There's two control degrees of freedom. So the operator will be specifying two set points, and as the control system is shown, the flow in set point and the flow and the level set point. These are the two set points that he specifies. However, the level set point is only a dynamic degree of freedom in the sense that it doesn't affect the steady state. It has only a dynamic impact, no steady state impact. And the flow in set point has a steady state impact as well as a dynamic impact. So we say that the control degrees of freedom of the process is 2, steady state operation degree of freedom is 1, dynamic degree of freedom is 1. So the two control degrees of freedom are split into 2. Dynamic degree of freedom 1, which is the level set point, and steady state degree of freedom 1, which is the flow in. Okay. Let's continue. Tanks in series. So there's 4 tanks in series. You've got 1, 2, 3, 4, 5 valves. So control degrees of freedom is 5. You put a flow controller on the first flow, on the inflow, and then you have level controllers oriented in the direction of flow as shown in the figure. So you've got 4 level set points and 1 flow set point, and these level set points, if the inventories are non-reactive, these level set points have a transient effect, have a dynamic effect, no steady state effect, and therefore we have steady state operation degrees of freedom is 1, which is the inflow, and dynamic degrees of freedom are 4, which are the level controller set points. Okay, let's have a heated flash drum. So the control valves are independent control valves are as shown there, and so the control degrees of freedom is 4. Now if you start looking at so you fix the heating rate, the inflow is fixed. As the fluid is heated, the tank gets pressurized and vapor is allowed to leave under pressure control, and as vapor leaves, the level goes down, or the level will change. In order to keep the level fixed, you adjust the outflow. So you can see there are 4 control degrees of freedom. Level of course has no steady state effect, so there are 3 steady state degrees of freedom, 1 dynamic degree of freedom. So okay, now here throughput is inflow, heating rate is what is deciding the vapor liquid split. I have noted pressure and level in brown because typically the steam header pressure is fixed and you're not free to change this set point. This set point is fixed. Because it is fixed, you're not free to change it. Therefore, it's not really a degree of freedom. It is there, and yet it is specified that the flash tank should be generating steam at such and such pressure. So the pressure is sort of fixed. So because it is fixed, you're not free to change. So in that sense, what the operator is free to change are the throughput, the flow through the system, and how much steam is being put to heat the system. So these are your steady state degrees of freedom. These are things that have no steady state effect or that are already fixed. Okay. Then we go for the non-isothermal liquid phase CSTR. In this case, you will have 3 valves: flow in, temperature controller adjusting the cooling rate, level controller adjusting the flow out. So control degrees of freedom is 3. Now because level affects the conversion and hence the steady state at which the process operates. So if you have a higher level, you will have a higher residence time, you will have a higher single pass conversion. If you have a higher single pass conversion, you will have less unreacted reactants in the outflow. If you reduce the level, you will have lower single pass conversion. Lower single pass conversion means you will have more unreacted reactants in the outflow. So this level set point has an effect on the steady state, and therefore control degree of freedom is 3, steady state degree of freedom is also 3. And for the control system that has been shown, the specification variables corresponding to these 3 degrees of freedom are feed rate, which is throughput, reactor temperature, reactor hold up or level. Yeah. Now let's come to, I think maybe the next one would be a distillation column perhaps. Yeah, it's a distillation column. So in this distillation column, how many control, well, the flow control is there, it should not be there, but that's okay. So there are 1, 2, 3, 4, 5, 6 control valves. So control degrees of freedom is 6. And then you put in these basic controllers. So you got feed flow control, reflux under flow control, reflux drum under level control, cooling rate, condenser cooling rate under pressure control. The steam is fixed or the steam is specified, and bottom flow rate under sump, bottom sump level control. Okay. Now typically you may decide that okay, in order to keep the split fixed, I'll control 2 tray temperatures. So you're controlling a stripping tray temperature by adjusting the steam rate. You're controlling a rectifying tray temperature by adjusting the reflux rate. Okay, so now in this case you can see the control degrees of freedom is 6, and the operator is specifying exactly 6 set points. 1, 2, 3, 4, 5, 6. Of these 6 set points, this has no effect on the steady state. This has no effect on the steady state because it is a non-reactive liquid level inventory. This has an effect on the steady state. However, you are not free to change. The column is supposed to operate at its design, not free to change. Yeah. So therefore, it's a degree of freedom, and yet you're not free to change it, so you're not going to count it. That leaves you with the remaining 3, this guy, and this guy. So you've got, typically columns will be analyzed in this fashion, that of the degrees of freedom that you've got, of the 6 degrees of freedom that you've got, column pressure and 2 level controllers take away 3, that leaves 3 steady state degrees of freedom. And those 3 degrees of freedom, steady state degrees of freedom, are as written here: throughput, stripping temperature, rectifying temperature, and then the other set points are, maybe I should change the color. Oh, sorry. How do you change the color? Arey yaar. There we go. So what kind of color do you want? We want a brown color. Well, this looks brown enough to me. And these guys have no effect. This guy I'm not free to change. Yeah. So the 3 steady state degrees of freedom are feed rate or throughput, stripping tray temperature, rectifying tray temperature, and or if you do not have those temperature controllers, then the degrees of freedom are reflux rate and reboiler duty. Okay, so that's a simple distillation column. Now we'll move on to the next unit, which I think is a plug flow reactor. We'll see. Yeah, so you've got vapor coming in, heated to the packed bed reactor inlet temperature. Exothermic reaction happens in the packed bed reactor, and the packed bed reactor is cooled. The hot reactor effluents are cooled and condensed. Whatever can be condensed is condensed and collected as liquid. So there's liquid outflow in the drum, and whatever are the non-condensables that cannot be condensed leave as fuel gas or flash gas. Okay, so that's my process. So let's see how many control valves we've got. Okay, so we've got 1, 2, 3, 4, 5, 6 control valves. Somebody may ask, why do we not have a valve here? Somebody may ask, why do we not have a valve here, here, and here? We don't have a valve here, here, and here because it is flow through a pipe. It's just that the plug flow reactor is a big pipe. Whatever is flowing in from here flows through the cooling heating tubes, through the packed bed reactor, through the cooler, and then ends up in the flash drum. So it's all one flow through a pipe, and that pipe could be large or small. Packed bed reactor is a large pipe. Cooling water or cooler and heater could be a bundle of pipes, and so on and so forth, but it's all essentially flow through a pipe, incompressible flow through a pipe. So you can set the flow at only one location, and that one location that we have chosen is this guy. Okay, so that is why we don't have. Okay, so now that we've got these control valves, so the control system is pretty straightforward. You've got feed flow controller. Feed is under flow control. Then you got manipulation of the heating duty to bring the feed temperature to the reactor inlet temperature. That's this guy's job. Then a reactor temperature is being maintained by adjusting the cooling rate, and then the hot reactor effluents, you want to condense it as far as possible, are cooled to maybe 10 degrees above the coolant temperature, and maybe it's a water cooled cooler. So if water is at 25 degrees Celsius, so maybe you're cooling everything to 40 degrees Celsius. So that's the job of this temperature controller. Whatever condenses is taken out as liquid under level control, that's this guy, and whatever does not condense is taken out as fuel gas under pressure control, that's this guy. Okay, so for the control system out there, what are my degrees of freedom? There's 6 degrees of freedom, and what are the 6 specifications corresponding to these 6 degrees of freedom? So there's production, reactor inlet temperature, there's reactor temperature, reactor pressure. Because the flash drum pressure is equivalent to the reactor pressure, there will be negligible pressure drop across the heater and the cooler. Okay, so reactor pressure, condensate temperature, that's this guy, and then flash drum level. And flash drum level has no steady state effect. Of course, if you increase or decrease the pressure of the flash drum, the reactor pressure will increase or decrease, which will have an effect on the conversion. So I'm including reactor pressure as a steady state degree of freedom because it has a steady state effect. So that's that with respect to this process. Now let's go to the next process that we are going to look at. It's a toy process. It's a toy process, but it's a very instructive process. So what you have is, let me walk you through the process. So what you have is fresh A. What you have is fresh A coming in, fresh B coming in. It's mixing up with the recycle stream. The mixed stream is going into a reactor. An exothermic reaction A plus B. A adds to B to give a heavy product C. Exothermic reaction, so some heat is removed in the cooling coil. That's this guy. And reactor effluent Single pass conversion is not 100%, let's say it's 30%, 40%, 50%. So there's significant amount of unreacted A and B in the reactor effluent. So this reactor effluent is sent to a column. Heavy C drops out down the bottom. A and B, which are lighter than C, go up, and these are recycled. So that's your process. And if you count the number of valves, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's control degree of freedom of 9. Of these 9, the column pressure is given. This level and that level, whichever controller that you put in, it's going to have no effect on the steady state. Column pressure is typically regulated by adjusting the cooling duty. So this guy is also taken out. So of the 9 degrees of freedom, 3 get taken out to fix the column pressure and the sump and reflux drum levels, and the sump and reflux drum levels have no effect on the steady state. So the steady state degree of freedom of the process, what you're really free to change, excluding the column pressure which is fixed, is actually 9 minus 3, that's 6. So the steady state degree of freedom of the process is 6. Now I'm going to show you a control system here, and it may take me some time to explain it. Just bear with me in case you. So let's see. So here's the control system, and let me just say that the way the control system has been drawn, let me walk you through it. You've got A underflow control. Oh, no. Sorry. Mistake. You've got A underflow control, and that is its set point. B flow is kept in ratio with the A flow, and there should be a line here. Okay, so you multiply the A flow by a multiplier, and this is the multiplier set point, and that gives the set point for the B flow controller. So B is maintained in ratio with A. There's a temperature controller that manipulates the reactor cooling duty to maintain the reactor temperature. There's a reactor level controller that manipulates the reactor outflow to hold the reactor level. Then on the column you've got the pressure controller, the level controller, top level controller, bottom level controller, and then you've got L by F ratio. This is L by F ratio, reflux to feed ratio. So you take the feed rate, multiply it by the L by F multiplier, and that sets the set point of the flow of the reflux flow controller. Okay, so you're fixing the L by F ratio, and there is a temperature controller. Here's the temperature controller that's taking in a set point. That temperature controller is manipulating the reboiler duty to hold a sensitive stripping tray temperature constant, and by holding a stripping tray temperature constant, what you're doing is you're not allowing A or B to drop down the bottoms. So this is indirect composition control. Inferential composition control is what it is referred to as. And let's pay some attention to this guy. You see, as per the stoichiometry of the process, 1 mole of A reacts with 1 mole of B. 1 mole of A reacts with 1 mole of B to give 1 mole of C. Okay, so if you're putting in 1 mole of A and assuming that the C is nearly pure or almost pure, you should be putting in 1 mole of B. However, there are always flow measurement biases. When a flow sensor is saying that the flow rate is 100 kilograms a minute, the flow may be 100, it may be 105, it may be 95. It's, there's always uncertainty associated with the measurement itself. Similarly, B flow may also be 100 or 105 or 95, and what if the situation is that actually this flow is 95 and actually this flow is 105? So then you have excess B going in, even though both the flow sensors are showing the flow rate is 100 kilograms a minute. So you see, with this arrangement, I am independently setting flow A and B in ratio with A. However, this does not guarantee reaction stoichiometry, because now in this case, like I'm saying, like shown here, the B is in excess. Now the temperature controller won't allow the B to drop down because B is lighter than C. So if B starts dropping down the column, the temperature of the tray will start going down. If the temperature of the tray starts going down, the temperature controller will say put in more reboiler steam, and that will not allow. So the steam will go up and that will not allow the B that is coming will go back up. Okay, so you don't allow B or A to drop down the column, and so the excess B will keep accumulating in the recycle loop. This build-up of excess B in the recycle loop will be reflected in, for example, the B composition in the reactor. The B composition in the reactor increasing. This increase in the B composition in the reactor is a sign of excess B accumulating in the recycle loop. Okay, so just like you have a tank, and if flow in is not equal to flow out, if flow in is not equal to flow out, then the level in the tank is increasing if flow in is more than flow out, or decreasing if flow in is less than flow out. Yeah. So to stabilize this system, what do? In the previous example, we took flow in as independent and put a level controller that manipulates flow out. Here what we'll do is put a level controller that manipulates flow in. So now in this case, flow out is independent, and the inventory that was drifting, which is the level here, that level drift in the level is indication of flow mismatch. So you measure the level and you manipulate the inflow or the outflow. In this case we are manipulating the inflow, so that in minus out is exactly 0. Similarly in this case, let's see, in the case of this ratio, A to B ratio, because A and B may not be exactly stoichiometrically balanced, the excess reactant is going to accumulate in the recycle loop. Therefore, that excess is detected by a drift in the composition of the reactor, and that composition is maintained by adjusting the A by B ratio. So this is the control system here. So we are maintaining the A by B ratio by adjusting. We are maintaining the stoichiometric feed balance by adjusting the A by B ratio in a feedback arrangement. Yeah. So that's the control system, and you can see, as far as the operator is concerned, the operator will be setting, control degree of freedom is 9, he'll be setting 9 set points. 1, 2, 3, 4, 5, 6, and then 7, 8 and 9. See, the brown ones, the levels have no effect on the steady state, and the pressure set point I am not free to change. So these magenta set points or the pink set points are corresponding to the steady state degrees of freedom. The brown set points are corresponding to the dynamic degrees of freedom, or fixed things that we are not free to change. Okay, so the way the control system is drawn, we have Oh, every time it's a problem, man. So we have flow, reactor level, reactor temperature, reactor composition, column reflux to feed ratio, column temperature, stripping rate temperature. These are the 6 steady state degrees of freedom. And then we have column pressure, reflux drum level, and sump level as the remaining 3 degrees of freedom that either have no steady state effect or we are not free allowed to change. Okay, so that's these 3 chaps. Excuse me, Jai Corona. Now until now we have been discounting non-reactive liquid levels. If a liquid level is reactive, it will have a steady state effect because it will affect the conversion. But if you have a liquid level that is non-reactive, we typically will require a level controller, and that level controller set point will not have a steady state effect, so it's called a dynamic degree of freedom. So in order to get the steady state degree of freedom, we discount number of levels that need non-reactive levels that need to be controlled. Until now, this is what we have been doing. Now let me show you an interesting case. So in this case, level must be controlled. So control degree of freedom is 2, dynamic degree of freedom is 1, steady state degree of freedom is 1. Dynamic degree of freedom corresponds to the level set point, and steady state degree of freedom corresponds to the feed flow in the control system that's drawn there. Now let's consider this guy. So here we have a tank, and liquid is circulating around the tank. Okay, and you've got a flow controller there, and someone may say that, oh man, because all levels must be controlled. There we go again. Because all levels must be controlled, let's put in a level controller that manipulates the flow out. But if you apply your mind, do you see that this level actually cannot be controlled? Because you make a change here, this flow changes, outflow changes by the same amount, so inflow minus outflow remains 0, so level doesn't change. So there is no cause and effect relationship. You can keep changing this flow and it won't make a damn difference to the level. If this flow is 0, level is whatever it is. If this flow is 100 kilograms a minute, it is what it is. If this flow is 1000 kilograms a minute, the level is still the same. So changing this flow doesn't affect the level at all, because there is a closed, the material is looping around the process in a closed circuit. There's nothing coming in, there's nothing going out, it's just looping around in a closed circuit. And you could have multiple units here and it would still imply the same thing. Okay, so when you have these closed loops where nothing is coming in and nothing is going out, in these cases the level must not be controlled. It cannot be controlled, and because it cannot be controlled, then whatever is the circulation rate, loop circulation rate, that remains the degree of freedom. You are free to set that. So in this case, level cannot be controlled, should not be controlled, and so the control degree of freedom is 1 here. Steady state degree of freedom is also 1. Level cannot be controlled, there is no dynamic degree of freedom. Alright, and a very interesting example of closed loop circulation we'll discuss next. Homogeneous extractive distillation. Now let me explain the process to you. You've got binary mixture AB. It is preheated, fed into the extractive column. This is called the extractive column. Extractive column. And this is called the solvent recovery column. So how should I write it? Solvent recovery. The solvent recovery column. Okay. So the feed goes into the extractive column. The entrainer or the solvent is heavy, so it drops down the bottoms of the entrainer or solvent recovery column. It is hot because it's heavy, so it's hot. So it loses some of its heat to the cold feed, preheats the cold feed, and the cooled entrainer is fed into the extractive column somewhere near the top but below the reflux. So maybe there are 5 or 6 trays here, then there's a middle section, and then there's a stripping section in the extractive column. Now because the entrainer is much heavier, the entrainer tends to go down, and the entrainer has the property of soaking one of the components, A or B, preferentially. For example, ethylene glycol preferentially soaks water. Triethylene glycol or DMSO is hygroscopic in nature, so it will preferentially soak in water. Okay, so if you have an ethanol water mixture, water will get soaked in by the entrainer. So the entrainer preferentially soaks in this example, B. So whatever B is going up, the entrainer goes down. The vapor leaving the top tray, because there's entrainer on all the trays, and it soaks in B, keeps soaking in the B. This is essentially B free. Yeah, so with the B free vapor, this vapor is essentially B free. And these trays over here, if there is some minor amount of entrainer that goes up, the reflux will essentially not allow the entrainer to leak up the top. Okay, so the middle section soaks in B, does not allow B to leak up, so prevents B leakage up the top, prevents B leakage. This middle section, this guy prevents entrainer leakage up the top. And what shall we? This guy, which is the stripping section, it prevents A leakage down the bottoms. Okay. Okay. So essentially, with these kinds of leakages being prevented, what you get up the top is pure A. What you get down the bottoms is an BE mixture. This BE mixture is a binary mixture. It is sent to the next column. The B being lighter than the entrainer because the entrainer is heavy. The B leaves up the top and the entrainer leaves down the bottoms. So this is the classic homogeneous extractive distillation sequence. Now let's draw its control system. So you've got feed under flow control. You've got the feed under flow control. On the column you've got reflux rate fixed, standard pressure control, level control, and then you've got a temperature controller that manipulates the reboiler steam or the reboiler duty. and the idea is this temperature is held constant so that a leakage down the bottoms is prevented. This AE mixture goes to the next column, and in the next column what we do is we've got same old. We've got pressure control, level control, we've got reflux underflow control, and then we've got reboiler duty being adjusted to hold a tray temperature so that B doesn't leak down the bottoms. And now we start thinking, okay, what about this guy at this level? Okay, so let's look at what we do with this level. We say, okay, we're going to control this level by adjusting the bottoms flow. This is actually the bottoms flow. This is all flow through one pipe. This is all flow through one pipe. This is all flow through a pipe. So one would say, okay, we'll put in a level controller like this. But if you think about it, look at the overall material balance of the process. If you look at the overall material balance of the process, what you will find is you're taking in an AB mixture, and then you're taking out pure A, and you're taking out pure B. The entrainer is simply going around the process in a closed circuit. And what is that closed circuit? Well, the entrainer comes in here, drops down, goes in here because it's heavy, it drops down. This is the closed circuit around which the entrainer is going. So it is just going round and round in the process with very, very minuscule amount, trace amounts, parts per million, parts per billion leaking out here, parts per million, parts per billion leaking out here. Negligible leakage. Okay. This is similar to your air conditioner, where you charge your air conditioner with the refrigerant, and that refrigerant actually evaporates and condenses and re-evaporates and recondenses and just keeps on evaporating and condensing in a closed circuit. And after 4 or 5 years, once the gas has leaked enough, you fill it up again, and then you're good to go for another 4 years, 5 years. Yeah, so that's how air conditioners work or refrigerators work. Okay, so here we have the entrainer going around in a closed circuit. So remember what I told you, if something goes around in a closed circuit, its level cannot be controlled. The same thing happens here. You see the entrainer being heavy, this is where the entrainer accumulates. This is nothing but the entrainer. The inventory of entrainer in the process is here. And if I adjust the bottoms rate, is going to come back in, and so there is no cause and effect relationship between the entrainer rate and the bottoms rate, entrainer level and the bottoms rate, and so the level at the bottom should not be controlled. So the level at the bottom of the solvent recovery column should not be controlled. Yeah, it should not. So you see, this level controller should not be there. So this should not be there. And so you set the solvent rate independently. And typically, if your feed rate is going to go up, the solvent must go up because you've got more B to soak up. So the solvent must go up in ratio with the feed. So that is what typically is done. So you have the solvent in ratio with the feed. That's this guy. And you also, to make sure that too much entrainer doesn't leak out the top in B, you make sure that the feed is, the reflux is in ratio with the feed. So that's what this guy is doing. And that's it. That's your control system. And in this control system, let us see how many control valves do we have. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 control valves. Of these 11, 3 levels need to be controlled, 3 level controllers. It's not 4 because this level is not being, it cannot be controlled. 2 pressures, that leaves 6 steady state degrees of freedom. Yeah, so that's precisely what I have written here. So there's 11 control degrees of freedom, 3 level controllers, 2 column pressures that are fixed. So the steady state degree of freedom is 6. And what are those 6 set points in the control system that has been shown? Let's look at those set points. Uh-oh. 1, solvent to feed ratio. 2, extractive column temperature. 3, reflux rate of the extractive column. 4, solvent recovery column reflux to feed ratio. 5, solvent recovery column stripping tray temperature. 6. These are the 6 steady state degrees of freedom. The other 3 correspond, the other 5, 1, 2, 3, 4 and 5, these 5 correspond to surge levels that have no steady state effect or set points that I am not free to change. Okay, so that's the control system and the degrees of freedom for this seemingly complex process. Okay, what I should write here is what are my steady state degrees of freedom? Feed flow, feed rate, solvent to feed ratio, temperature of column 1, reflux of column 1, L by F for column 2, temperature of column 2, 1, 2, 3, 4, 5, 6. These are your 6 degrees of freedom. Specifications corresponding to the 6 degrees of freedom that the process has. And then of course the other 5 are pressure of column 1, pressure of column 2, level control of the reflux drum for column 1, level control for the sump of column 1, level control of reflux drum of column 2. So these are the 5 process variables controlled using the other 5 control valves. Okay, so that takes care of that. This is an exercise that I'd like you to do. It's a Petliuk column, so I'll explain what a Petliuk column does. A Petliuk column takes in an ABC feed and it does an AB-BC split, the easiest possible split. So A is the light key, C is the heavy key. So what happens is the top vapor that leaves the process is AB, very little c. The bottom liquid that leaves the prefractionator, this is called the prefractionator, this is the prefractionator. The bottom that leaves the prefractionator is BC with very little a. And now when you distill this vapor again, this section prevents B from leaking up, so at the top you get pure A. This section prevents A from going down, so you will get pure B. This section prevents C from going up, so you get pure B. This section prevents B from leaking down, so you get pure C. Yeah, and the thing about Petliuk columns is because you do the easiest separation first, its thermodynamic irreversibility is much less because the composition profile doesn't have as much remixing as you would have if you had, you know, ABC. You take A up the top, BC down the bottoms, and you distill again. You take B up the top and C down the bottoms. That's called the direct split. Direct split, or you could have the indirect split where you do ABC, take AB up the top, B down the bottoms. Take this guy, split it again. Take A up the top, B down the bottoms. This is called the indirect split. So the direct or the indirect sequence has got more remixing, and I don't want to talk about why it is so. You'll have to look at the composition profile, internal composition profile, be that as it may. The point is the Petliuk column will, because of it is inherently less it has inherently less irreversibility compared to the direct or the indirect sequence. So the reboiler duty of the Petliuk column is usually significantly less than the direct sequence or the indirect sequence. Yeah. So what I want you to do is, for this sequence, calculate the control degrees of freedom, the steady state degrees of freedom, and also start thinking about what kind of a control system we'll have on this. Okay. That's it. That is it for today's lecture, and I think this is a good time to call it quits. So let's stop our recording and see how good or bad it is. Oh, 56 minutes. That's quite a long lecture. Okay, so thank you so much for your attention. Ek minute. Maybe I missed something. Yeah, maybe. Shift F5. Okay, so of course the valves are shown here, but you have the control degrees of freedom, but figure out the steady state and the dynamic degrees of freedom, and a control system that will do a good job. Okay, and specifications corresponding to those degrees of freedom, like we have done for other processes. That's the exercise that is there for you. Oh. तो साला बंद कर दिया क्या? बंद किया कि नहीं किया? I think it is recording. Okay, so this is the last slide that I have, and I wanted you to take a good look at this. So given a process flow sheet, what are we doing? We are essentially placing control valves on each adjustable flow, and we are counting the number of control valves, and the number of control valves happens to be the control degrees of freedom. And then the steady state operation degrees of freedom is obtained by subtracting out from the control degrees of freedom the number of non-reactive surge drum level controllers, where you have to install a level controller, because those levels will not have any steady state effect, minus any other fixed conditions. For example, if the column pressure is given. And once this subtraction is done, that gives you the steady state operation degree of freedom of the process. So that's the intuitive degrees of freedom approach that I use all the time, and I found it to be quite effective, useful, direct, no beating around the bush. And I hope you will also be able to develop some skill in terms of looking at a flow sheet and figuring out its degrees of freedom, and then working around to thinking what should be controlled, what should be specified corresponding to those available degrees of freedom. So that's the lecture here, and I think I'll end now. Thank you very much for your attention. This has been a long lecture, but I hope it was worth it.